as we have studied till now that Coulomb's law is used to find the force between 2 point charges. In that condition, the force is given by capital F is equals to K, which is a constant, Q1 into Q2 upon R square. So this is your Coulomb's law. Now, if in that condition there exist more than 2 charges, then will this law is applicable? No, this law won't be applicable. Now, I'm talking about point charges. That means I'm talking about particles. But if we move on to matter, then matter consists of very small particles. That is, the particles are spread all over. So is it possible to find the force between all these charges? No, it is impossible. So in that condition, the Coulomb law fails. The physics that we talk about, the physics consists of small and big sources. Even it consists of the sources of various shapes and various sizes. So in that condition, the Coulomb's law is not able to give us the final law or the final conclusion that how these sources are being tackled out. Now, in one condition also, the Coulomb's law fails, that he states that there occurs a force of attraction or a force of repulsion between the 2 point charges. But how this force is created, that is, what is the effect around the charges that creates the forces? In that condition also, the Coulomb is silent. So now, for better understanding, we need to move on some different concept. To understand the most complex situations of the charged particles more than that of the Coulomb's law, we need to focus that what Michael Faraday states. The Michael Faraday put a very shocking concept, and this shocking concept is a real one. In that he emphasized that there are many charges. Okay, the charged particle he talked about, that every charged particle consists of some effect around it, and he named this effect as electric field. So the main topic which I am focusing or emphasizing upon is your electric field. Now, what is this electric field? The electric field is the definition. I am talking about the definition. It is basically the measurable effect which is created around the charged particle. Now, what is this measurable effect? The measurable effect which I am talking about is electric forces. Electric forces are the same forces that draws power to your home, that drives your computer, that charges your computer, and everything is the electrical forces which is concerned to the electricity. Now, how this force or how this effect is calculated, or how we came to know that this particular charged body has some effect around it. Can we see this effect? No, we cannot see. Can we feel this effect? No, we cannot feel. If there is a charged body, so we cannot feel any effect around it. So there is a common phenomenon which can tell you that there is some effect created around the charged particle. For that, we need to take a positive charge which is represented as plus Q. This positive charge is also called a source charge. It is called source charge because it is used to generate the electric field around it. It is plus Q because the intensity or the magnitude of the charge in this particular condition or in this charge is very high. So now the electric field is generated around the positive charge, that is plus Q. Now, in order to check the electric field or the electric effect around this plus Q charge, we need to bring plus small q positive charge near to that of the plus Q charge. Now, this small q charge is basically your test positive charge. This test positive charge is used to test the effect which is created around the positive Q charge. Now, in this condition, when this positive Q charge is brought near the source charge, then there occurs some force between them, and this force is called the force of repulsion. This force of repulsion is exerted by the source charge on the test positive charge and draws the test positive charge away from it. Now, what is this force of repulsion? This force of repulsion is the electrostatic force, and this electrostatic force we have already studied in the Coulomb's law. So this is what we have studied till now. So two important points that you have to keep in mind is that the first important point tells that the test positive charge should be very, very small. The second important point is that the test positive charge should be always positive. Now let us come that what these 2 points mean. I'm talking about the first point, that is the test positive charge is very, very small. It is considered very, very small so that the electric effect which is created around this small q should be very, very small, or it is negligibly small so that it does not affect the electric field which is created by the source charge. This is only the reason why the magnitude of the test positive charge is very, very small, so that it does not hinder with that of the positive q charge. Now, the second point tells us that if the test positive charge is always positive, then the force between the two charges depends upon the polarity of the source charge. If the force charge is positive, then the force of repulsion exists. If the force charge is negative, then the force of attraction exists. Now, after this fundamental topic of electric field, we are moving on to the main topic that we call electric field intensity. In other words, we can also say that electric field is also called electric field intensity. Now, what is this electric field intensity? It is the intensity of the electric field, or we can say it is the strength of the electric field. It is a very important term for us to understand. In this condition, if I ask you that how the strength of the electric field is notified, then it is notified by the force which is created on the test positive charge by the test positive charge. So, confused? Don't worry about that. I am going to formulate a very simple formula for you. Now, the electric field intensity is given by capital E. This capital E is the electric field intensity, equals to force, capital F upon small q. What is force in that condition? This is the force which is experienced on the test positive charge by the source charge. Small q is your test positive charge. So, this is the formula for electric field intensity. Now, capital F, I already told you it is the force. What force? Electrostatic force. Electrostatic force, Coulomb's law. Okay. Whenever I talk about force or the electrostatic force, so I talk about Coulomb's law. In that condition, according to Coulomb's law, that is capital F is equals to K, Q1, Q2 upon R square. Putting this capital F on this equation, you will get your answer. That is, cancel out all the terms which are common, and finally you will get the equation of electric field intensity. That is, it becomes now K times of capital Q upon R square. So, this is the formula for electric field intensity. So, now electric field intensity is clear to you. Depending upon this formula, what can be the unit? Now, just look carefully of this formula, that is K Q upon R square. Q has the unit Coulomb. R, which is the distance, has the unit meter. The square over it becomes meter square. So, the electric field intensity unit is given by Coulomb per meter square. Another unit for it is volt per meter. So, this is all about the electric field and the electric field intensity. But I already told you that electric field intensity is the strength of the electric field. That means if the electric field intensity is high, then electric field in that particular portion is also very high. How this electric field is high? Electric field is only high when the charge is high, because we have already seen in the formula that is E is equals to K times of Q upon R square. That is, E is directly proportional to your capital Q. If Q increases, that is, the charge increases, so the electric field intensity also increases. We can see by the diagram. This is the diagram, okay. In this diagram, you can see from the diagram there are 3 point charges, A, B and C. Now, just notice the area or the lines which are drawn around A, B and C. Of the point A, if I am talking about, so the point A consists of smaller charge. So, the electric field around this capital A is also rare. Okay, you can see the lines which are drawn away from capital A. These lines represent the electric field intensity. If it is rare, so that means the electric field is also less. If it is dense, so the electric field is also high. So, the charge capital A has less charge. That means the electric field intensity is also less. Now, look at the charge capital B. In that condition, this body capital B has some increased amount of charge. In that condition, you can see that the electric field intensity around capital B also increases, which is shown by some dense lines. These lines are basically electric field lines, which we will explain later on. Don't worry about it. Now, come to the third diagram, that is point C. Now, the charge is increased more. In that condition, the line becomes more and more dense. That is, the electric field lines around point C becomes more dense. That means the electric field intensity becomes maximum. So by this diagram, we can see that on increasing the charge, the electric field intensity also increases. If electric field intensity increases, then that means the electric field around that particular point charge also increases. So by drawing conclusion, we can say if there are many charges, so you don't need to find the electric field intensity across each charge. You need to place just a positive test charge near to all the charges and find the corresponding electric field intensity in that condition. So this is all about the electric field.